If you are like me, the concept of quantum physics has probably evoked fear from the first time you heard the name. Much like calculus or hydrodynamics, this subject sounds intimidating before you even know what it entails.
Today I'm going to focus on two of quantum physics' main ideas, wave-particle duality and Schrodinger's cat. Let's start at the beginning. You most likely get excited when December rolls around because it means a break for the holidays. You may not have realized that this month holds yet another event that deserves celebration, the birthday of quantum physics.
Let me explain.
On December 14, 1900, physicist Max Planck developed an equation that described the reason that radiation from a glowing body changes in color as its temperature increases. Contrary to popular belief at the time, Planck's equation implied that energy could only exist in discrete units, much like matter, rather than arbitrary amounts. Said another way, you can divide a quantity of light energy in half over and over again until you reach a small chunk of energy that cannot be divided further. Planck called each of these chunks a quantum. Through this discovery, Planck unknowingly took the first step towards the creation of a realm of physics that causes even the greatest scientific minds to cower. In fact, Planck himself did not fully understand his discovery.
Despite developments in this field such as the uncertainty principle developed by Heisenberg and quantum leap theory developed by Bohr, quantum physics did not really find a prominent place in the scientific world for quite some time. This all changed with the double slit experiment. Let's start with a large-scale explanation of the experiment.
If you were to shoot tennis balls, one by one, at a barrier that has two slits and you record with the detector where the balls that manage to pass through the slits impact a second barrier, they would create a pattern much like the one shown here. However, at a subatomic scale using electrons rather than balls, something much different happens. The electrons do not land only behind the two slits as was seen with the tennis balls. Instead, they land across the detector at varying degrees of frequency. Scientists were shocked. They determined the electron behaves like both a particle and a wave, which when reaching the barrier splits in two, releasing separate waves from the other side of the slits. The interaction of the two waves creates the interference pattern at the detector. Much like the interference of ripples in water, create areas that are strengthened or diminished.
This concept of particle-wave duality introduces an idea that scientists struggle to comprehend even today. If an electron is both a particle and a wave, and the wave passes through both slits, the electron must be in two places at once. Yes, two places at once.
In an effort to understand this occurrence, scientists placed detectors on the sides of the slits with the hope of catching these tricky electrons in the act. However, when this was done, something incredible happened. The electrons acted only as particles, passing through one slit or the other and creating a pattern on the detector much like that created by the tennis balls. This occurred even when the detectors were moved and were switched on midway through the electron's movement. Even more astonishing, when the detectors were kept in place but switched off, the electrons once again acted as waves and the interference pattern appeared again. This occurrence is the foundation of the superposition principle, which states if we are not measuring the position of an electron, it is in all possible positions simultaneously. This superposition vanishes if we measure a position.
To explore the superposition principle further, let's discuss Schrödinger's cat.
In this theoretical experiment, a cat is placed in a box with radioactive material that has a 50% chance of decaying and killing the cat.
Based on the superposition principle, when the box is closed, the cat is both dead and alive. Only when the box is opened and the cat is observed does it revert to one state. I told you you'd be fine. Because this goes against common logic, this thought experiment shows how odd the principles of quantum physics really are.
It is undeniable that the concepts in quantum physics bring about almost inconceivable implications relating to quantum technology, the presence of alternate realities or worlds, and even the teleportation of particles. This young field of science is key to unlocking the ways of our universe, and I encourage you to research it because we still have so much to learn.